Shapley value, and these are the topics for this lecture. Definition and interpretation. So informally first, the Shapley value is the fairest way to share the value Vn of the grand coalition N. Each agent I's share of the value of the grand coalition is its Shapley value V sub V comma N of agent I. So this is the total value of the coalition, grand coalition, and each agent I receives this amount. And this is in some way the fairest way to share this total value. The Shapley value is the only solution concept that satisfies all axioms of fairness. And we will discuss that later. But what this means is that the Shapley value is unique. Formally, the Shapley value of an agent I is its average marginal contribution in the coalition game V comma N of that agent I to all possible ordered subsets or coalitions not containing agent I. This is the expression or how we denote the Shapley value of agent I. Psi sub V comma N I. Note that this Greek letter can be pronounced either psi or psi. Both are equal. Now, what exactly is an ordered set here? I use the word ordered subset. So ordered sets, these are two different ordered sets. They contain the same elements, but the arrangement of the elements or the ordering of the elements are different. So these are two different ordered sets of the same size. All these are different ordered sets of the same size. Now the number of coalitions of size C is given by n minus 1 choose size C, which is equal to n minus 1 factorial divided by size C factorial times n minus size C minus 1 factorial. And so this is the expression for the Shapley value. So the Shapley value of agent I is the average marginal contribution. So the marginal contribution of agent I to any coalition C is delta VCI. This is the average marginal contribution. Now we are applying a weight when we're doing this averaging. We are summing over all possible coalitions that do not contain I here, but we apply this weight to each coalition C, and the weight is inversely proportional to the number of coalitions of the same size as C. And then we normalize so that all the weights would add up to 1, so that this indeed is the average marginal contribution. We divide it by n factorial. So that's the expression for the Shapley value. So here's one way to interpret this Shapley value. Psi of agent I is 1 over n, summation over all coalitions, n minus 1 choose size C inverse, that is 1 over n minus 1 choose size C times marginal contribution to each coalition C of agent I. And this is equal to 1 over number of agents and summation over all coalitions C that exclude agent I of marginal contribution of agent I to coalition C divided by the number of coalitions of the same size as C. So this is the random arrival interpretation of the Shapley value. Now look at this figure here. This is the set of all agents. I'll refer to it as the agent pool. And this is a time axis. It begins with time instance 0, then 1, then 2, 3, until n, where n is the total number of agents. Now, at time instance 0, we begin with the null coalition. And at every time instance, a new agent is drawn from this agent pool and random and removed from the agent pool and then allowed to join the coalition. So suppose at random in the first time instance, we pick agent 4 from the agent pool. So it's removed from the agent pool and the coalition is 4. And then suppose at the next time instance 2, we randomly pick 7 from the agent pool. It's removed from here, and then the coalition, the new coalition that is, becomes 4, 7. And so we proceed until time instance n. So we see that every time instance, the size of the coalition increases by 1. Here, at time t equals 0, the size of the coalition is 0. Then at time instance 1, the size of the coalition is 1. Here at 2, the time instance 2, the size of the coalition is 2. And suppose this is the coalition C at a certain time. That certain time is equal to the size of T. Let's say at the next time instance, size C plus 1, agent I is randomly picked and it joins the coalition, so that the coalition now is C union I. And the time instance increases by 1. So now I've replaced the coalition with the sizes, the values of the coalition. So this is the value of the coalition C at this time instance. And at the next time instance, the value of the coalition is V C union I. And the difference is V C union I minus V of C, which is equal to the marginal payoff of agent I in this particular sequence. Now the expected value, we carry out this over any number of times. So the expected value of the marginal contribution using this random arrival interpretation is equal to the Shapley value. The number of permutations of this sequence 1 through n is n factorial, and the number of permutations of the agents before the arrival of I is C factorial, or rather size of C factorial, and the number of permutations of the agents that arrived after I is n minus size of C minus 1 factorial. Related to the Shapley value is something called the Banzhaf value, but the Banzhaf value doesn't weight the marginal contribution like the Shapley value does. So we don't consider ordered subsets here. The Banzhaf value is simply the average marginal contribution of an agent to a coalition, and all coalitions are given equal weightage, so that beta I, the Banzhaf value of I, is 1 over 2 to the n minus 1 of summation over all coalitions, not ordered coalitions, just coalitions now, delta VCI, the marginal contribution. Here's the first example. we have three agents, and we'll call them A, B, and C, lowercase a, B, and C. And these are three people. They begin at this point, and their destinations are 5 kilometers, 6 kilometers, and 10 kilometers away from this point where they begin. And they need to share a taxi cab. So they begin from this point, and then all three of them here take a right until this point. At this point, this is A's house, so agent A is dropped off, and B and C share the right until this point here where agent B is dropped off, and then C goes all the way from here to here, this point here, which is the final destination. And the cost is $1 per km for the shared taxi. So from the origin to this point A here, there are all three agents in the cab, and so it's fair if, since the total distance is 5, the fare is $5 until this point A here, and since all three agents were in the taxi, it's only fair that each of them divide the total fare 5 equally amongst themselves. Now at this point, agent A is dropped off, so from this point A to the point B, which is 1 kilometer, the agents are only B and C, and so it's only fair that these two agents, B and C, share the fare of $1 here equally, so that each pays $0.50. Now from B to C, it's only agent C who's in the taxi cab, and so only C should bear this fare. So only C should bear this $4 here. Now let's look at, let's say, agent B. So what's agent B's fare here? 5/3 plus 1/2, which is equal to 2.1667. And it turns out that that's also equal to the Shapley value. If you use the Shapley value, you would arrive at the same figure, 2.1667 for agent B. Suppose we begin with the null coalition and agent B joins the coalition. For the null coalition, there's no taxi fare included, and when B joins the coalition, then we have to take a taxi from this point all the way to B, which is $6. So the marginal contribution to the null coalition of agent B is $6. Now suppose we start with this coalition containing A only, and B joins the coalition. Now when A alone is in the coalition, the total taxicab fare is $5. When B joins, it becomes $6 because B has to go further away, and so the difference, 6 minus 5, is the marginal contribution of agent B to the fare, and that's equal to 1. Now let's consider C. C alone would have to go all the way here so that the taxi fare would be $10. If B joins the coalition, then it's BC now. B is dropped off at this point, and the taxi still has to go all the way here. The fare is still $10, so the difference is 0. B contributes no increment to the total fare by joining C. So the marginal contribution of V is 0. Likewise, if A and C alone were to share the taxi, then the total cost would be $10, and agent B joining, since it's going to be dropped off here, contributes no increase to the fare. Therefore, the marginal contribution of B to AC is also 0. And so this is the formula for the Shapley value. 1 over 3 factorial times size of each coalition factorial times 3 minus size of C minus 1. That's 2 minus size of C factorial times marginal contribution of B. And so null coalition. So let's consider the null coalition that corresponds to the first term. This is the marginal contribution to the null coalition. And so this is 0 factorial and this is 2 factorial. The second term here is this coalition here, A, and the marginal contribution of A is of B to A is 1, and we have this is the coalition containing A alone, that's equal to 1 factorial, and this is 3 minus 1 minus 1, that's again 1 factorial. So this is the second term, and likewise we have the third term and the fourth term here. And replacing all the values here, we get again the same value, $2.1667. Example 2. We will compute the fare values using the common sense interpretation first in A, and then in B using Shapley value random arrival interpretation, and then in C using the analytical expression for the Shapley value. So here is the problem. There are 4 units, B, C, D, and E. B, C, D, and E. Note A is not an unit, so it's not an agent. Only B, C, D, and E are the agents. And all of them, these 4 houses, must be connected to this source O. Maybe this is the source of energy or water supply or something else. And so these are the possible links that must be established. Now, link OA is costs $20. Link AE costs $18, and so on. So these are the different links, and these are the costs of the links. And so how should the agents, these 4 agents or these 4 units, B, C, D, and E, share this cost? Now let's look at each link. So OA is shared by all 4 agents. So these are the sharers of this link OA. Therefore, it's only fair that this cost of $20 must be divided equally between these 4 agents so that each agent pays 5, or each unit pays $5. AB is shared by only B and C. And so it's only fair that the 2 units, B and C, share the total cost of 16 equally. So each pays $8 for this link AB, and so on. So these are the sharers of each of these links. These are the total costs, and so if we divide the total cost amongst the sharing units, then this is how much each has to pay. So these are the amounts that each unit pays. B shares OA and AB, so it pays 5 plus 8, which is 13. C shares this, and this, so it pays 5 plus 8 plus 10, which is 28, and E likewise pays $14. And next, in the random arrival interpretation, we'll look at how to compute the fair value or the fair payment or cost of agent E. So the random arrival interpretation. These are all possible permutations of the four agents or four units. And it's only this agent here, E, whose Shapley value we shall try to compute. Now, first we'll look at the case where D arrives before E. So D is already there. So this part of this link has already been established. So when E arrives, its marginal cost or marginal contribution, whatever, is 0. And there are 12 such cases where D arrives before E. And these are colored in blue. Now we'll consider the opposite situation where D arrives after E. Okay, when D arrives after E, so we don't even care for the cost of this link because D arrives after E and E doesn't require this link. And likewise, E doesn't require any of these links, so we ignore those cases too. So this AE in these cases must be paid by E. Now the question is, if B or C have arrived before or after, so whether this part of the cable is already there or if it's not there. So this is case 2. Here, B and C, at least one of these two units are there before agent E arrives. There are 6 such cases. And in this case, this link is already existing. So agent E has to pay only this cost, 18. So that's the marginal cost of agent E. And there are 6 such cases, 6 permutations. Now, when B and C are not, at least one of these two units is not present before the arrival of E, in that case, E has to pay this total cost, 38. And there are 6 such permutations. Therefore, the Shapley value of E is value of 0, 12 permutations, 6 permutations, it pays $18, and in 6 permutation, it pays $38. And the total number of permutations is 24, and this works out to be $14, which is what we had originally computed for that same agent. Now let's compute the Shapley value of the same agent using the analytical expression. The first row contains all the coalitions with 0 agents. That's only the null coalition. The second row contains all the coalitions with 1 agent, and the third coalition with 2 agents or 2 units, and the fourth row contains 3 units. And in each case, we'll compute the Shapley value to the coalition of the unit E. So when C is null, no unit exists. Adding E to the null coalition, you have to establish these 2 links. So the cost is 20 plus 18, which is 38. When the coalition contains B alone, so B exists, in the coalition, adding E to it would require a cost increment of 18. So the marginal contribution of E is 18. Likewise, for each of these other coalitions, I have shown the marginal contributions. The non-zero marginal contributions are colored red, blue, purple, and green for clarity, and the Shapley value works out to be 14 as in the previous two cases. Next, the Shapley value is efficient. In other words, the sum of the Shapley values of all agents in the Grand Coalition equals the value of the Grand Coalition. And the proof can be established readily using the random arrival interpretation and the binomial theorem. Theorem. In a convex game, the Shapley value lies in the core. And another theorem, in a superadditive game, the Shapley value is an imputation. And these will be discussed in a later lecture. Example 3. Now this is the glove market game. These are the agents. There are two right gloves and one left glove, R1, R2, and L. And the value of a coalition equals 1 if the coalition contains one left and one right glove, and 0 otherwise. So I have listed the values of each coalition here. This is the game. These are the different coalitions of gloves, and these are the corresponding values. Now, we want to determine a payoff vector R1, R2, L. What is the cost of each glove R1, R2, and L, and they will be represented as lowercase r1, lowercase r2, and lowercase l. In barycentric coordinates, this triangle represents all payoffs or all values of the agents when R1 plus R2 plus L equals 1. And since individual rationality can be ignored because the value of each glove alone is 0, therefore this entire blue triangle represents all imputations. Now let's look at the core. Group rationality must be satisfied. So R1 plus L must be equal to 1. That's this red line here. Likewise, R2 plus L should be 1. That's this here. And so this point of intersection is the core. 0, 0, 1. It's a singleton. The core of the game is this red dot. Now let's compute the Shapley values of the gloves. Each row here is a permutation of the 3 gloves. Now, for R1, it's only in this row L, R1, and R2 where adding R1 to the previous coalition gives a value of 1. So L is the coalition, and then R1 is added. The marginal contribution of R1 is 1 because now we get a pair, and so it's only this case we consider 1 out of these 6 where the Shapley value, the marginal contribution of the R1 glove is 1. So the Shapley value of R1 is 1 over 6. Now, Shapley value of R2 can be computed exactly in the same manner. It's only in this row where adding to a coalition R2 will give you uh, uh, a marginal contribution of 1. So we again get 1/6. Now, in all four cases here, the first four cases, we have at least one right glove. And so in each case, adding the left glove increases the value from 0 to 1. And so 4 over 6, that is 2 over 3, is the Shapley value of L. So we plot the Shapley value here. This is the Shapley value. Now, as you can see, the Shapley value is different from the core. It doesn't coincide with the core. It's this point here. But it lies in the set of imputations. So the Shapley value is an imputation. Why is it not equal to the core? That's because this is a non-convex game. It's super additive. That can be verified very easily that this game is a super additive game. And so the Shapley value is an imputation. However, this is not a convex game. It might not have a core in general, but in this particular example, the glove market game, we do have this point as the core, but the Shapley value is not in the core. That's because this is not a convex game. Example 4. Now we'll look at our familiar game here, which we know is convex. These are the coalitions, and these are the values of the corresponding coalitions. Now, we use this expression to compute the Shapley value of agent 1. So the agent's Shapley value turns out to be 3. This 1 here corresponds to this 1. This 3 here is 5 minus 2, and this 5 here is 7 minus 2, and this 4 here is 10 minus 6. Likewise, the Shapley value of agent 2 is 3, and the Shapley value of agent 3 is 4. So the Shapley values are 3, 3, and 4. Now, we have already seen that this red trapezoid represents the core of this game. And this is where the Shapley value is. It lies in the core because this is a convex coalition game.